This is work on deep learning that's inspired by fundamental ideas in physics, and that I think will also have applications to actually to many different sciences. So I'm going to talk about what we call gauge equivariant convolutional networks. These are a generalization of convolutional networks that have been extremely successful in the analysis of images and audio and other kind of Euclidean data. And this generalizes that to manifolds. Before I talk about gauge equivariant convolutional networks, I will discuss some earlier work on what we call group equivariant convolutional networks, just to set the stage of what of this for this work, and also to introduce some concepts that we'll be using later. And then I will talk about the general theory of gauge equivariant convolutional nets, and then I will discuss a specific instance of it, where we can analyze, for example, omnidirectional images that you might find in self-driving cars, or signals on the surface of the Earth or in the sky, anything that's essentially spherical. Gauge equivariant convolutional nets is a joint project with Maurice Weiler and Berkay Kichanaoglu, as well as my supervisor Max Welling and Berkay's supervisor Arnold Smulders. So first, group equivariant convolutional networks. So as many of you will know, progress in deep learning is mostly driven by what you could call intuition-driven empirical exploration. So people have some idea about what might work, they try it and see if it works, and if it doesn't work, they play around with it. If it still doesn't work, then they publish it. So that's fine. It does lead to tremendous progress. But of course, it would be nice if we could actually understand what's going on. And we've learned in AI generally that trying to hand engineer the solution to a problem is usually not the way to go. You know, classifying cats and dogs, or healthy cells and cancerous cells using domain knowledge is extremely difficult. And so people have now gone on to the data-driven approach. But I think that we need sort of a hybrid where we have high-level design principles that are not specific to, say, classifying cats and dogs, but that are still you know, introducing some prior knowledge into the design of neural networks. So the principle that I've been looking at mainly in my PhD can be summarized like this. It's equivariance to symmetry transformations. So in many problems, you know that certain transformations shouldn't affect the results, and you can use that to improve your neural networks. And indeed, the most successful neural networks already embody this principle, even if they don't necessarily always talk about it in these terms. So if your data is, for example, images and audio, the most successful methods are convolutional neural networks, which are translation equivariant. And as I'll show in a second, we've recently generalized that to what we call GCNNs, where it can also take into account other groups of transformations, like rotations, for example. In graph data, you have permutations of nodes that preserve the graph structure, and graph neural networks, they embody this symmetry. And you can generalize it even further to manifolds that I'll talk about today. So the first idea in this direction is what we call the regular GCNN. So the idea here is a convolutional network uses convolutions to detect features. And there's another mathematical generalization of that called a group convolution. So what if we use that instead? So I'm not sure about everyone's level of familiarity with deep learning, but in a convolutional network, what you do is you take some input image and a number of filters that are learned, and you convolve this small filter with the image to produce a feature map. And then you apply some nonlinearities, and you repeat the process for many layers, and eventually produce some output. So what we do in a GCNN is that instead of just translating this filter over the image and detecting similarities everywhere, we also apply other transformations, like, for example, rotations to this. So in a very simple example, you might rotate this filter 4 times by multiples of 90 degrees. convolve it with the input image, and it produces 4 feature maps that we call orientation channels. These encode the similarity of this image to the different rotations of this filter. And then what you can do is you can ask, okay, what happens if we rotate the input image? If we do that, and then we apply the same operation where we convolve with the rotated filters, you again get 4 orientation channels. But as you can see, 2 things happen. First of all, these feature maps are rotated relative to these ones. But also, the feature maps, they undergo a cyclic shift. So, for example, if you have some horizontal structure in the original image, and you rotate the image, then what was picked up by the horizontally oriented filter here, say this channel, is now picked up by the channel corresponding to the rotated filter, which is this channel. So the feature space has a different transformation law, you could say. Whereas the input, each channel is just rotated independently. In the feature space, you have a rotation and a permutation of the channels. And this kind of phenomenon we're going to see over and over again in different and more general forms. So what do we do in the second layer? Well, this layer was appropriate for these kind of scalar input maps. But these features, which we think of as a function on the group of transformation, for each translation and each rotation, you get a value. These functions transform according to what mathematicians call a regular representation of this group. That is to say, each channel rotates, and there's a cyclic permutation among the channels. So for the second layer, we're going to follow the same logic. We have a filter, which now has 4 input channels. And we're going to rotate it 4 times. But what it means to rotate such a regular filter is that we rotate each channel, and we permute the channels in this cyclic way. And it turns out if you do that, and you convolve with the 4 times 4 filters that you produce this way, you get 4 output channels that again have this same transformation law. So the good thing about doing this is that whereas in a normal convolutional net you would have to relearn the different orientations of the same filter, here that there's much more parameter sharing, which leads to better statistical efficiency. And in practice this is true even if you augment your data with transformations. Yeah.
I just want to clarify, you use the word channel with the RGB channel, what do you call idea? Or,
yeah. So yeah, that's correct. So in the input you might have RGB channels. Here it's just a grayscale image, so 1 channel. And then in general, in a convolutional net, you have some number of channels, 64, 128, whatever. And here we just show 4. Of course, in practice we use many more, but each channel detects some kind of feature. So we call it a feature channel. And in GCNNs, in addition to these feature channels, which correspond one-to-one with the filters, you now also have orientation channels that correspond to different orientations of the same filter. Okay. So in the last layer, if you're doing something like segmentation, you could, for example, sum over these groups of 4 channels, which gives you an output feature map that behaves again like a scalar function, like a single scalar channel, in that if you rotate the input image, then the output is going to rotate. So for example, if you're doing segmentation, you're trying to say for each pixel in the image, what is this? If you were to rotate the image, you want the segmentation output to also rotate. And if you want invariance, you can just sum over all the spatial pixels. So as I said, there's a general mathematical theory about this, which allows you to do this for, in principle, any group, although there can be implementation difficulties, of course. And that allows you to do all sorts of variants. So for example, you can do this on a hexagonal lattice, where you have a 6-fold rotational symmetry that you can implement without any kind of interpolation, which is cumbersome in practice. Or you can do it in 3 dimensions. So this is a picture of the group of symmetries of a cubic filter, or a cube in general. And I'm not going to explain the details of this figure, but the basic, what I want to convey is just that this is a pretty complicated group. Cube is a simple object, but the group of symmetries is pretty complicated. It's non-commutative. If you rotate around the z-axis and then around the diagonal axis, that's different as rotating around the diagonal axis and then around the z-axis, for example. And it has a lot of elements. It has 24 elements. So if you apply the general theory to this group, then you will find that you have a lot of weight sharing. Now, for each filter, you get 24 channels that share weights. And this channel cycling phenomenon that I talked about generalizes. And in this case, if you apply one of these rotations to your input, then the feature channels, these 24 channels, they will undergo a permutation that you can actually read off from this diagram. So for example, the red arrow corresponds to a rotation around the z-axis. If you apply that to your input, then these 24 feature channels associated with each one of the cubes here, they will be permuted according to the red arrow. So we tested this on the problem of pulmonary nodule detection in CT scans, and we found that it works really well. In that it gets about a 10x improvement in data efficiency, meaning if you train a GCNN, for example, on 3,000 samples, you get roughly the same performance as a normal CNN trained on 30,000 examples. And that's true across various orders of magnitude of data set size. And it's the baseline, the CNN, was actually a state-of-the-art model that ranks highly in competitions. It uses data augmentation and all the usual tricks for making convnets work well. You can also generalize it to curved spaces. So for example, in earth sciences, in computer vision, in astrophysics, cosmology, etc., you might encounter some signal defined on a sphere, on the earth or in the sky. And so we developed a generalization of convolutional networks that works on spheres. And the basic idea is very simple. So the planar convolution, you can understand it by saying that the output feature map at a particular point in the plane is the value there is computed as an inner product between the input feature map and the filter shifted by whatever point you're looking at now, by that translation. So we think of the output feature map as a function on the translation group, which is just the plane. So in spherical CNNs, we follow the same logic, but now the space of moves that we apply to our filter is the rotation group. So the feature map is a function on the rotation group SO3. And so whereas in the input you have plane times plane equals plane, now we have sphere times sphere equals some three-dimensional manifold, which is the rotation group. And you can also convolve these kinds of signals again. So you can build a convolutional network this way. And that works quite well. But it's also, it's pretty compute intensive. So one thing I'll talk about later in this talk is a way to build a much faster version of this. All right, so what I've talked about so far is what we call regular GCNNs, which are just based on this idea of taking the convolution that's used in convolutional networks to detect patterns everywhere and replacing that with a group convolution to not only detect them anywhere, but also in any orientation, or in theory also in scale or other transformations. And what we're going to do now is we're going okay, so what we did is we replaced this convolution, and then we looked at the feature space and said, okay, what transformation law does this feature space have? But we can do something different. We could say, what if we just say, I want this feature space to have a particular transformation law. For example, I want it to transform like a scalar field, or I want it to transform like a vector field. These are of course, these are concepts that are used all throughout science, particularly in physics, but not at all in machine learning. But let's say we want to do that, and then we design a layer that will satisfy this equivariance property. If my input transforms like this, my output will transform like a vector field does. The regular representations, you can think of a special case of this. In the very first image I showed, you have a plane, and on the plane lives a field of four-dimensional quantities, and these four-dimensional quantities, they have a transformation law that says if you rotate, there will be a cyclic shift of the coefficients. But a scalar, for example, is an invariant quantity, and a vector has another, this is a three-dimensional quantity that has yet some other kind of transformation law. Again, this is very useful from a statistical standpoint, because now you have this transformation law in your feature space. You can do clever weight sharing. You can say, if I detect this pattern in one orientation, I also want to be able to detect it in any other orientation. And only because you have this notion of a transformation law of your feature space is it possible to do that. Then we have what we jokingly call the special theory of equivariant convolutional networks, where we generalize this to convolutional networks on any homogeneous space. So a homogeneous space is just a manifold, where for any 2 points on the manifold, you can move one into the other using some symmetry transformation. So the plane is a homogeneous space because you can translate any point to any other point. The sphere is a homogeneous space because you can rotate any point into any other point. We can build GCNN for this kind of space by choosing some group of symmetries G, some subgroup H. That forms the quotient G over H, which is the base space of the theory. So for example, the sphere is a quotient of the rotation group and a subgroup. If that doesn't mean anything to you, don't worry about it. This is just one slide. The final ingredients of this theory is to say, okay, we're going to choose a fiber or a feature space. So at each point in this manifold, we're going to attach a vector space that will contain these feature representations. This vector space will have the same dimension as the number of channels in your convolutional network. And this feature space, it comes with what's called a representation row of H. So that's basically for each transformation, say for example each rotation, we have a big matrix of number of features by number of features that tells us how to transform these features under rotation. Okay, so the reason we call this the special theory is because there's actually a very precise analogy between this kind of mathematics and the special theory of relativity, which deals with similar kinds of structures. And actually, the second part of the talk on gauge equivariant nets, you could think of that as the general theory where we generalize these structures further. So we have one theorem that says, first proven by Condor and Trivedi for scalar fields, and then by us for more general fields. It says that equivariant maps between, just read that as fields, so spaces of fields, vector fields, whatever, can always be written as convolutions using some equivariant kernel. So from a deep learning perspective, what this says is this notion of fields that we sort of pulled out of our hat and that nobody else is using yet in deep learning, it's not artificial. If you want to reuse this concept of convolution, which has been so useful, then you're going to have to interpret your feature spaces as spaces of fields. And we also have a full characterization of this space of equivariant kernels, which you need to actually implement this. You can read these papers for details. All right, so on to the latest stuff. This is about gauge equivariant convolutional networks. So there are two motivations for this work. One is that we want to generalize convolutional networks to manifolds. So in the sciences, you'll find many kinds of signals defined on manifolds, and we want to be able to apply deep learning there. And this is basically the motivation from what they call geometric deep learning, which tries to do this. And then there's the motivation from equivariant deep learning. What I've been working on is to just generalize these equivariant nets beyond these very symmetrical manifolds like spheres and such. So we want to generalize convolution. How do we do that? So that first attempt that I've been talking about so far is to say, okay, we're going to do weight sharing via global symmetries. We're going to take a filter somewhere on this manifold. We're going to apply a symmetry transformation, and then we have a filter at another location that shares the same weights, the same parameters. We're going to detect the same signal there. And that works on very symmetrical manifolds, but not on slightly less symmetrical or totally unsymmetrical manifolds. So here you see the icosahedron. Let's say we look at this region. If we have some local filter there, we can apply a symmetry transformation to move it to any other corner point, but not to, say, the interior of a face. So if you just want to share weights by symmetry transformations, then you can only do that across the orbits of this symmetry group, not across the whole manifold. So that idea doesn't really work. And then there was another idea that's been proposed, which is to say, okay, let's do weight sharing via parallel transport. So parallel transport is something you can define on any smooth manifold. And it's visualized here for a vector-like quantity. So we have a vector at A. We can basically move it over the manifold without changing it. Of course, it's changing in the embedding space, but looked at from the manifold, it's not changing. But hey, what happened when we get back? It's actually a different vector. So
are you assuming that the curvature is the same throughout the space?
No, in this example it is, but in general, we don't assume anything like that. Yeah. And more generally, it's the case that parallel transport between point A and B depends on the path you take to go from A to B. So if I have a filter, say at one position, and I want to just shift it over the manifold with parallel transport, it works fine if there's no curvature, if it's a flat region, like this is a consistently aligned filter across this flat piece of space. But if you take a curved space, for example, if this were the corner of your icosahedron, which has some curvature in this point, and you cut it open and then lay it flat, and you transport over the flat surface, you see, this edge is identified with this edge, so as you move it across, it's rotated. So it's hard to give a consistent way of how to orient your filters everywhere on the manifold if you want to use parallel transport to define that. And then there have been some methods that actually deal with this in a correct way, but not in the most general way. And actually, some work by Jean Brunat was one of the first to do this. So there's, for example, the idea of spectral convolution, where you can define a generalized convolution via the eigenfunction of a Laplacian or a graph Laplacian, if you approximate your manifold with a graph, for example. And this works well, but it only gives you rotation invariant quantities because the Laplacian is an invariant operator. And actually a simplified version of that is called graph convolution via message passing, which is pictured here. So we have our graph that maybe covers your manifold. In each point we have some feature vector. And in each layer we're going to compute an update for each feature vector. So let's consider this feature vector fi. And what we do is we take these feature vectors from the neighbors, multiply by some learned matrix, and sum them all up. And clearly that's going to be invariant. This operation doesn't care about which neighbor is sending each message. And if you think about what that would mean for, say, if you did this on the plane, if you think of your pixel grid as a graph, and you apply a graph convolution, it would mean you can only use circularly symmetric filters, which is, of course, very limited. You can't even detect edges, for example. So this is a sound definition because it doesn't matter how you orient the filter because the filter is rotationally symmetric, but it's limiting. And then there's an improved version called Geodesic Convolution. And so here the idea is that you extract at each point, you extract a local patch from the manifold and consider the signal on that patch. And you match that local signal with a local filter, which you rotate with some number of rotations. And then you take a maximum over the responses to all these rotated filters. So that sounds very similar to what I was talking about in the beginning, where we take a filter. In that case, we rotate it just 4 times. You can imagine doing it more times. And it's what we call scalar to regular convolution. So you have a scalar input feature map, and then you have a regular feature map, which has all these orientation channels. But then what they do is they take a maximum over these orientations to, again, produce an invariant quantity, a scalar. And this, we found in other work, is actually more limited kind of representation than the regular to regular layers that we use in a GCNN. Okay, so what the conclusion of all this is that on manifolds, it seems like there's no natural way to define an orientation at each point in the manifold. We are forced to make some arbitrary choice. And actually this fact is what motivates a lot of differential geometry, theory of fiber bundles, and gauge theory, and so on in physics. So here's a picture to explain some of these basic concepts. We have a manifold. Again, I'm just showing a sphere because it's simple, but it works on any manifold. It's called M. And we have, say, two different coordinate systems on this manifold, shown in the red and blue lines. And associated with each of these coordinate systems is a set of frames. So a frame for the tangent space at a point. You can also just freely choose your frames to have any other kind of orientation. In the end, it's all arbitrary. The coordinates are arbitrary. The frames are arbitrary. Such a choice of frames is called a gauge in physics. And now the key thing to notice is, let's say we have this point. If we look at it in terms of local coordinates, it's this guy. Now, if you have a vector field that we describe in terms of these local coordinates, then at this point we have a vector whose coefficients are described relative to these two red basis vectors. And now, even though it's the case that in the other coordinate system, which also covers this point, these basis vectors are the same, you can see on the manifold they're not the same. So there's a red coordinate frame and a blue coordinate frame. And so if I have a vector described in this coordinate system, and I want it in this coordinate system, I have to apply some transformation. For example, a rotation. That's called a gauge transformation. You want to change the gauge. And so one more thing to say about this is that not only is this choice of gauge something we have to make and it's arbitrary, it's also impossible to make a global choice if you want to do it smoothly. Oh, so some thing is not showing up. This says parallelizable. So this is a non-parallelizable manifold, which means that there is no smooth field of frames that you can put on this manifold that doesn't have any singularities like the one you're seeing here. So if you want to, for example, take your filter and you want to orient it relative to a frame, let's say this field and one orthogonal to it, then at the North Pole you would put filters at very different orientations, even though they're very close, which is very different from how you would be doing it around the equator, even though, geometrically speaking, this is not any special point. This is just an arbitrary artifact of our coordinate system. So we have to work with local charts and local gauges. All right, so then the idea of gauge equivariant convolutional networks is this. Like before, we will attach a feature space or fiber to each point P in the manifold. The dimensionality of the space is the number of channels of your convolutional network. And this fiber has a representation attached, associated with it that tells you how these features will change if you change the gauge. And then we want the network layers to be gauge equivariant, meaning if you were to change the gauge in your network, you redescribe all the coefficients relative to this new frame, then all your features would also transform according to this representation row. All right, so how do you do that? Well, here's the setup. First, we're going to cover just the scalar case, which is not so useful in practice, but it's a little bit simpler. So we have a feature map F, single one, which we think of as a function from the manifold to the real numbers. We have a kernel, which we think of as a function from Rd, where D is the dimension of the manifold, say 2, to R. And we can identify this Rd with the tangent space at P via the gauge, right? If you have two numbers and you have a frame on the tangent space, that allows you to associate, the gauge allows you to associate Rd with the tangent space. So you can think of this either as a function on Rd or as a function on the tangent space. And we're going to parameterize a local region around each point using the exponential map, which takes a tangent vector at P, and it follows the geodesic, the straightest curve, in the direction of V for 1 unit of time with a speed V. So basically, this gives you some nice coordinate system of the local region around P. And then we can define the gauge equivariant convolution as follows. We just the convolution of this kernel and your feature map at a point P in the manifold is an integral over Rd, or your tangent space, of the product of these two things. So F evaluated at, say, this point times whatever the kernel weight is at that tangent vector. And then you can see that this will be gauge invariant, or equivariant is a special, invariance is a special case of equivariance for scalars, if and only if the kernel is rotation invariant. So that's what we saw before. If you match a, if you want to produce one invariant quantity, the only way to do it that's independent of how you orient the filter is to make the filter rotation invariant. So just a circular kind of filter. Well, that's very limited, so you can generalize this. And now we have a field f that's locally described as a function from the manifold to R to the C1, where C1 is the number of input channels. So at each point we have this vector. And now our kernel, we model that as a function from RD, or the tangent space, into our C2 times C1, where C2 is the number of output channels, and C1 is the number of input channels. And then the convolution takes this form. We take this matrix, so it's basically the same equation as before, only now this is not a scalar but a matrix, and it multiplies a feature vector to produce an output feature vector that we sum over all the spatial positions. And this this feature vector is parallel transported from QV to P. So we take a feature vector, we parallel transport it all to the center point for which we're computing an output now, multiply by these matrices, and that gives us our output feature vector at P. And this is equivariant if and only if your kernel satisfies this constraint, which says that if you rotate the kernel, you get the original kernel except conjugated by these two transformations on the input and output sides. All right, so that's pretty abstract. It's probably best to read the paper if you want to really understand it. But let's look at an example. So I'm going to talk about icosahedral CNNs. So before I mentioned spherical CNNs, and these are very useful. Spherical signals arise everywhere, but actually the spherical CNN that we have developed so far is somewhat slow. And on this manifold, because of its very regular structure and its local flatness, it turns out you can implement a convolution on this space very efficiently, reusing all the existing deep learning primitives. And it's only relatively small distortion. And we notice also that in practice, this still works very well on spherical signals. So what we're going to do first is we're going to set up some local charts. So we have here our icosahedron, our manifold, with a grid on it of, basically you can think of these as hexagonal pixels with 6 neighbors. We divide this up into local charts, like for example, this gray region corresponds to this one. We flatten it out, and then we do a skewing transformation on this, which gives you basically, allows you to map each one of these pixels into one square pixel here. And this is a kind of representation that your computer likes and that deep learning is based on, rectangular images. So we map images on this thing to a representation like this, where each region here, each region of size 2r by 2r plus 1, where r is the resolution of the grid, corresponds to some region here. And what you can see is a point, for example, on this edge. Let's say this edge here. It is represented in multiple charts, right? So this green line is to be identified with this green line. So the pixel that lives on this green line on the icosahedron, that's one pixel, but it has multiple representations because the charts overlap. And that's going to be very important. So in a normal convolutional network, when you have your filter, you can only produce a valid output if the filter fits within the image in its entirety. So what people usually do is they do a little bit of zero padding around the image, and then the output that you produce with your convolution is the same shape as the input. So we have to do something similar here, but in this case, the border of each chart corresponds to pixels that also live in another chart. So these pixels that are colored in this image, they are in one-to-one correspondence with the pixels here, except for the corners. So all we need to know a signal on here is to know all these colored pixels. But then if we want to do a convolution on this rectangular grid to simulate the convolution on here, we have to pad this. And the way we do that is we take each pixel here, and we map it via the inverse chart to the icosahedron. And then we map it back via another chart to somewhere where, to a chart where this pixel lies in the interior of the chart. And then we look up the value there, and we copy it to wherever we were going. You can do this very fast using one single indexing operation. And then we have the property for this thing that for every pixel in the interior of a chart, all the neighbors are also present in this image. Okay, so that's the first part. We call that G padding. It sounds complicated, but it's actually pretty simple and fast to implement. And one more very important thing to mention here. If we transition, for example, if we have a pixel on this edge and we want to copy it to this edge here to do padding, then there's a gauge transformation involved because the local frame on here might not correspond to the local frame on here, as we saw before with the case of the sphere. So when that happens, you have to apply a rotation to your feature, which in the case of a regular feature, of course, with say 6 orientation channels, corresponds to this cyclic shifting again. And then there's the second important part of the algorithm, which is kernel expansion. So we derived before in this general theory that for the convolution to be equivariant, the kernel has to satisfy this equivariance constraint. And the way that's implemented in practice is very simple. If you have, say, a scalar input feature map, you have one hexagonal pixel. We think of these grids as being hexagonal grids, right? Because every pixel has 6 neighbors. So we have one hexagonal pixel, and we just rotate it 6 times. And that gives us a kernel that has the property that if you rotate each of these channels, it's the same as cyclically shifting among these channels. And for the regular to regular case, we have a bunch of filters. We have a filter with 6 input orientation channels. And to expand this into an equivariant kernel, we rotate it 6 times, meaning we rotate each channel and we do a cyclic shift, and that produces a convolutional filter bank like this. And if you then then each of these hexagonal filters is represented in a square grid like this. You have a hexagonal region, it just corresponds to some region in your square grid. And to do a hexagonal convolution, you can just do a 2D convolution on this grid. And that's something that's been extremely well optimized and super fast and scalable. How am I doing on time? Until half, right? Yeah. All right. Then because you all like classifying digits, we did some toy experiment on digits that are projected on this icosahedron, but I won't go into detail. The main takeaway is that these regular to regular maps really do work better than scalar to regular or just scalar to scalar. And both this G padding and the kernel expansion are necessary for good performance. And also the non-equivariant models do not generalize well to rotated data if they haven't been trained on it. And even if they have been trained on it, they don't do so well. All right. Then a more serious problem is climate pattern segmentation. So there are certain climate models out there that people use to simulate all sorts of variables related to the climate. Don't ask me too much about it because I'm not an expert, but it's important, I hear. And in these simulations, certain events might occur that we would recognize as, say, a tropical cyclone or an atmospheric river, which is certain weather events. And then the task here is to take these spherical measurements of, I don't know, temperature, wind direction, etc., and to basically, for each pixel on the sphere, say, is this pixel part of a tropical cyclone, for example? And we tested on that, and we find that we outperform the existing methods that do this by quite a margin. And again, the regular to regular type maps that sort of preserve orientation information and don't make the features invariant, they work better. And we did a similar experiment for omnidirectional image segmentation using the Stanford 2D 3DS data set, which has 1,400 omnidirectional images, plus where each pixel has RGB and also depth. There are 13 classes. And we tested against a baseline, which is a UNet, or actually we didn't do this, but this was Jiang et al. They reported this baseline, UNet, which is a standard method for segmentation that takes a big image and in a number of convolution layers downsamples it. So each pixel in these high-level feature maps, they have a very big receptive field, and then they upsample it again to produce an output segmentation masks. And they produced a spherical variant of that using a method that's unrelated to what we're doing, but also a spherical convolutional UNet. And we generalized that using our method, and we're also getting better performance, although these numbers are still preliminary. They were produced yesterday, and we haven't yet tuned all the things in our algorithm. All right, so to conclude, gauge equivariant convolutional networks are sort of the most general kind of convolutional networks that you can define on manifolds that only depend on intrinsic geometry. It naturally generalizes both the group equivariant networks as well as certain previous convolutional nets on manifolds. And there are very interesting connections to mathematics and physics via the theory of principal fiber bundles that I haven't talked about much. Our first implementation of this idea for the icosahedron is extremely scalable. So we think that in principle, such a chart-based approach could scale to high resolution planetary scale data. And it gives good results on benchmark problems.